We are going to be discussing our final project titled Biomedical Search Engine for the Big Data Analytic class at Columbia University. Our team is composed by George from the School of International and Public Affairs, Mohammad from the Department of Electronic Engineering, and myself, Jose, from the Data Science Institute.
The UMLS, or Unified Medical Language System, is an initiative by the National Library of Medicine, which is a part of the National Institute of Health. The National Institute of Health dates back to the late 1800s when it was set up by part of the U.S. Department of Health and Human Services. The National Library of Medicine actually predates the National Institute of Health. It's from the 1830s, and it's the world's largest biomedical library. They formed the UMLS in order to integrate biomedical terminology and standardize it across a number of entities, as well as have common classification and coding standards, and provide a number of resources as well for looking at biomedical terminology.
Given the UMLS, which is a quite dense, raw data set, we wanted to make it accessible to any user by creating a website or a search engine that allows the user to input their query. We classify it, and then we output whatever is relevant to that query. So that includes definitions, relationships to other concepts, and also like a visualization of what they want to see.
The dataset itself is composed of three main parts. The first is the meta-thesaurus, which is what really contains the meat of the dataset. It's over 1 million biomedical concepts from more than 100 sources. And how these concepts relate is defined by the semantic network, which has over 130 different categories and more than 50 different relationships that each of these concepts are sorted into. And finally, it's composed of the specialist lexicon and the lexical tools, which is a number of common resources and tools for parsing and using this dataset.
Our system is hosted by Amazon Web Services. These slides show the URL that provide access to our project main site that contains general information about the project, including a link to our search engine. Our algorithm takes from 20 to 25 seconds to classify. To save some time, I'm going to show a preset example of our system using asthma as the text search. At the moment, our classifier had already classified our search and is providing us with the selection of concepts to choose from that are related to asthma within the semantic type or classification assigned by the classifier. The concepts can be seen in this drop-down. So let's say we're interested in general asthma. I'm going to select general asthma, and I'm going to go ahead and press select. Now that we press select, we're seeing that the results of our search show us that we select asthma. Our classification, or the semantic type that our classifier provided, was disease or syndrome. We have a definition of asthma with relevant information. You can see that we had links to external sites as well as symptoms of asthma, as you can see here. And we also have more relevant information related to asthma. We also provided an egonet of asthma that we can see here in a very interactive graph, and we can see that asthma is highlighted red, and the font of asthma was increased compared to the rest. This is very interactive. Like I mentioned, we can zoom in to asthma. We could see other related concepts. We could rotate the graph as well. So this gave us a very interesting tool to take a look at relationships with asthma and different concepts. We also provided this relationship as plain text, as you can see at the bottom of the page.
When a user enters the query inside their text box, the first thing that happens is it goes through a query cleanup process in a PHP script. These words are sent to a normalizer, and this normalizer, it separates the string into multiple words and also sends the normalized string itself to a Mahout trained classifier contained inside Hadoop. This classifier is based on naive Bayes. This sends back a class to the MySQL query generator, and the separate words also head there. The query generator creates a bunch of MySQL commands, which are sent to MySQL containing the dataset. This outputs information that the user can select from in a drop-down menu, specifically the concept that they want. When a concept is chosen, it's sent to IBM System G, which contains all the nodes and edges of the entire concept semantic map of the UMLS and outputs a JSON specific to the concept. Plotly, which is created by a Python script, visualizes the JSON content. The graph and MySQL info is finally shown on the output web page. When an input enters the PHP script, let's say you have the words heart disease in women. And let's try that out right now. You hit search. Now what's doing in the background is first cleaning up this query. It removes the in and it makes it all lowercase. So the output would be the second orange box. And then this gets entered into the word normalization, which alphabetizes them and separates the words. So this actually outputs four things. One is disease heart women, which is a normalized string that gets sent to the classifier. And then there's the three separated words, disease, heart, and women, which are sent to MySQL. And if we look back, we have this result. We basically can select it. It will show the corresponding results.
We train our algorithm with two sets of features, the UMLS normalized words and the UMLS normalized strings, which are a group of words. I want to focus your attention in the statistic area of these screenshots, in particular the accuracy and reliability. Looking at these statistics, we see that the normalized strings had a higher accuracy than the normalized words. So we decided to use the normalized strings as the feature set to continue training this algorithm. Now when deciding whether we want to use bigrams or trigrams, we can notice that in this case the accuracy of both are very similar. However, the reliability for the bigrams is higher. So we're going to continue using bigrams to train this algorithm further. Now when selecting the model, we are comparing or we train two algorithms, naive-Bayes and complementary naive-Bayes. And in this case, we see that naive-Bayes has higher accuracy and reliability, so decision in this particular case was a no-brainer for naive-Bayes, of course. Now that we have the model, we try to increase the accuracy by optimizing several of the parameters of this model, and we finally have an accuracy of 89.55%. That's the accuracy of our final classification, which is implemented in the final system. So once the user enters his search text and the classifier provides a semantic type for this text, our system proceeds to execute several layers of MySQL queries to try to find an exact match or a combination of terms to try to find a similar match related to the user's search within the classification provided by our algorithm.
So what's the importance of classifying a concept considering that it already has semantic types associated to it? Suppose a user looks up the word headache. Given our search engine results, you have headache as a selection and the classification is sign or symptom. Now if the user looks up headache Aleve, so this time they want to look up a clinical drug related to it rather than the condition itself, the classification is clinical drug. And the result can be shown as follows. So you have Aleve and headache and all the results that are associated with them together. Lastly, the user looks up headache for propranolol. This combination actually does not exist in the UMLS database, but the way the MySQL queries are held, it's going to classify it as a clinical drug anyways, and then it's going to look up combinations, if not look at the separate words and see if anything's associated with it. So in this case, headache is the result that it aims at because it can't find these two together. And the results show headache in a clinical drug setting. So it will display relevant results, specifically any drugs that headache is associated with, such as Aleve headache pill, Bayer headache relief, or, Sudafed.
IBM System G outputs a JSON file that we read into a Python script. The Python script parses the JSON file to identify the nodes and edges around the query that make up its network, and it highlights the query for easy identification and visualization. It maps these nodes and edges into a Kamada Kawai three-dimensional dynamic visualization that we then pass on to the website for the user to be able to view and manipulate in order to get to know the network better. So we believe that we achieved our objective. We took the UMLS data set, which is quite dense and can be difficult to work with, and we represented it in a accessible and meaningful manner through a biomedical search engine. So this search engine allows the user to input a single query and see the possible matches for it. It also allows the user to see the relationships to other biomedical concepts and use those relationships to potentially make decisions or find real-world relationships that they can use. Moving forward, possible ways to build on this project are to improve the search queries or possibly through adding a second classifier for concepts, organize the relationships in a possibly cleaner visualization, and create links between the relationships so that the users can see the UMLS information pages or other information pages that are relevant. This project will be suggested and can potentially be used quite soon by the New York Presbyterian Hospital. Thanks.